Welcome everyone. Despite the coronavirus, we all are here from home, I suppose, at least many of us. And we can start with the webinar today. Thank you to Dr. Jonathan Dungus. And here we start. As always, we have 1 hour, including questions and answers. Please go ahead, Jonathan. Thank you.
Great. Thank you for having me here in this seminar. I haven't been, oops, sorry about that. So I hope my internet connection can stand up to this. Kids might run in because we have to do homeschooling. So sorry about that. Well, you know, I'm coming from this topic from the Potsdam Institute and the Stockholm Resilience Center, thinking about interacting tipping elements and these types of things for quite a long time now. Basically, since I finished my PhD in 2014, and then I started a project funded by Leibniz Association on this called the Dominoes project, together with Ricarda Winkelmann from PIC and Jobst Heitzig. And so we've been working on these topics in this project since. So it's kind of still running until next year. And with a number of PhD students, postdocs, and collaborators also in the social sciences at the GESIS Institute for Leibniz Institute for Social Sciences, which is called GESIS in Cologne. And I'm also kind of an associate collaborator of the TIPES project. I haven't been able to attend many events yet, unfortunately, but I hope there might be some more exchange in the future. Right, so today I want to talk about where we come from in the Dominoes project into this topic. I'll give an intro to climate tipping elements, which basically I'm doing this quickly because I suppose you all know that, but it's kind of showing a bit where we are coming from into this topic, then I'll talk about some work we did on the Antarctic ice sheet as a tipping element as an example for a process-based study that we did. I'll talk about climate feedbacks that are induced by cryosphere tipping. I'll talk about interactions between tipping elements from a more theoretical conceptual standpoint, and then kind of about the network analysis of tipping interactions and the potential for tipping cascades to emerge possibly under global warming. And then finally, I'll talk about a little bit different project, moving now from the climate system to social systems, to positive or desirable tipping points that might help to drive decarbonization, climate change mitigation, and how we integrate this into a more broader look into World Earth system as a complex system. Right, so basically starting it's important to realize that global warming is kind of unfolding not only in a quantitative space of temperature between, let's say, 0 or up to 5, 8, 10 degrees of global warming in the further future if it's not mitigated, but it's also unfolding on a fast pace. So here we see how the Earth system went from the last glacial maximum 20,000 years ago to the beginning of the Holocene. There's the deglaciation. The Holocene was a relatively stable climate episode, and then even in the paleoclimate data, we see this kink around at the Industrial Revolution, where the temperature starts moving up, and then when we look into observational data, we see this as well, and then climate projections really show these are a bit outdated. Sorry about that. It's still the A1B, one of these old emission scenarios, but it illustrates that the warming is not only quantitatively important, but it's also up to 100 times faster than the natural warming after the last deglaciation. This warming can lead to the crossing of critical thresholds and tipping points in certain parts of the Earth system. And one that is, of course, studied very well is the Atlantic meridional overturning circulation, where critical thresholds exist in the, for example, in the freshwater, forcing input into the North Atlantic, which comes from rivers running into Arctic rivers running into the ocean, but also from melting of the Greenland ice sheet currently. And the circulation may potentially tip from a state where it's on to a state where it's much weaker. And currently there's a lot of indications that the circulation is weakening in the past decades. But of course, it cannot be proven at the moment whether it's already tipping down or it's just moving downwards on the upper branch. It's a very simple way of talking about that. Of course, just an example. A second example is ecosystems that include, that have been discussed as potential climate tipping points, such as the Amazon rainforest, for example, where rainfall received by the forest precipitation can have critical thresholds that lead to transitions in ecosystem state, regime shifts in ecosystem state, but also boreal forests, for example, and other ecosystems are increasingly discussed as potential tipping elements in a climate context. And there's various formal definitions and ways of defining what a tipping element is. One very simple way to look at it that I sometimes like to use when explaining it is that it basically means and can cause a big change in the system state. And this is, of course, a very simplistic way of talking about it. But the idea is that the small change can either be in a parameter, in a control parameter. It can be in state. For example, if noise-induced tipping, if noise pushes the system over its unstable manifold, the system can fall down to a different state. And in bifurcation tipping, of course, it's a small change in parameter that can lead to this transition. But of course, there's also other types, such as rate-induced tipping, for example. And this formal definition that I have in this box up there, this is the one that Tim Lenton and John Schellenhuber and others developed in their paper in PNAS 2008, which basically has this essence that a small change to the system can cause a big change at a later time. Now, this is one of these maps of potential tipping elements, some of which are better understood than others, and there's a lot of debate whether some of these systems are or are not really tipping elements. And as I understand, this is also part of what you're doing in the TIPES project, and partly also what we're doing in the Dominoes project. So very interesting, and there's many different versions of this map and maps by other people where some of these elements are included or are not included. And this, to me, seems still to be continuously changing and showing that the science is really in progress there. This is now showing that the potential critical threshold ranges of these different tipping elements, and this links up to the temperature evolution graph that I showed before, and it shows where these critical thresholds are thought to be compared to this past temperature evolution of the climate system from the last glacial maximum up to possible Anthropocene futures. And one interesting observation is that I think it seems that the locations of these tipping thresholds, particularly this first cluster of tipping elements that are possibly switched within the Paris range, it seems that they might have actually influenced these discussions that have led to the Paris Agreement in the end. A lot of some of these threshold ranges really started already 1 degree or a bit more of global warming, but certainly below 2 degrees and also below 1.5 degrees. There's also two more clusters one could think. One which includes more circulation and biosphere tipping elements starting here at around maybe 4 degrees of global warming, and then a third group which again includes more cryospheric elements, the Eastern Arctic ice sheet, permafrost, and Arctic sea ice at much higher temperatures. And it has been studied from the very beginning. I mean, when right after Tim Lenton published this paper in 2008, there was a study by people from PIC and elsewhere, Kriegler 2009, who did an expert elicitation on potential interactions between tipping elements, because the idea, the question is whether the tipping of one element could potentially tip other elements, like in a domino chain. And here in this figure for the Steffen 2018 paper, Ricarda and I put together some kind of an update of what was in this Kriegler paper, actually taking the expert knowledge on interactions possible interactions between tipping elements from the Kriegler paper and some updates to the literature that were published later, and also putting these temperature threshold ranges as a color scale here. And this is of course a complex system. It looks a bit like a network, which also kind of motivated us to do a certain type of network analysis to this system. I talk about that later. And it's also interesting when you look at it in this geographic way to note that it seems a bit like at the low end tipping threshold cluster, including Greenland, sea ice, and alpine glaciers, for example, it's really located mainly in the northern and southern polar regions. Then the intermediate tipping range, 3 to 5 degrees, seems to be mostly in the tropics and the mid latitudes, while again the high temperature cluster is again located more at the high latitude. So there might be, one might even think about that as an oscillation. When temperature rises, this goes from the Arctic more to the tropics and then back to the Arctic. But of course, this is really a hypothesis. But this picture seems to suggest something like that might possibly happen under unmitigated climate change. Now, this is a final introductory slide. In this trajectories paper by Will Steffen that we contributed to, there's a controversial figure that basically hypothesizes how this stability landscape of the Earth system, if you think about it that way, could look like, and it asking for the possibility of whether there maybe is something like a planetary threshold that separates different possible futures of the Earth system. For example, a more interglacial type state that the Earth system could remain in, or something which is more a runaway climate change type of world. However, I must admit that I'm also personally I see this as a strong hypothesis, and I don't want to advocate anything like that here. I'm just what my interest is really in understanding these tipping elements better, and how particularly the effects that the interactions could have, and whether or not this leads to such a landscape or a different landscape is then an open question that needs to be answered by this type of research. So let's move to a concrete case of the Antarctic ice sheets as tipping elements. And this is a picture of the collapse of the Larsen C ice shelf, where a huge rift developed and led to this, at least to the partial collapse of that ice sheet, or the start of that collapse. And these types of ice shelf collapses, they have been moving from the north to the south on the Arctic Peninsula over the past decades, and seem to be an indication that there's something really, climate change is having impacts possibly there in Antarctica already. That's kind of a quite visible type of dynamics that leads to impressive pictures like this one. And it's possible to understand these dynamics in going on in ice sheets, really using process-based simulations, leading even up to continental scale simulations of ice sheets. And I pick the Ricarda Winkelmann and her team that we are working with in the Dominos project. They are running this dynamic ice sheet model PISM that can simulate, really based on basic physics principles, the dynamics of the ice in on the Antarctic continent. And this is an example of such results, which shows ice surface velocities in blue colors and ocean temperatures in close to ice shelves in this other color scale on the left, and showing that if you compare this to observational data, it turns out that these models can simulate the observed properties of the Antarctic ice sheet, such as ice surface velocity, for example, but also ice thickness, calving rates, and so on and so forth, really, really well. So there's they are really well validated, and it's meaningful to do future projections with these types of models as well. And this is now a summary of a huge number of computational experiments that Yuli is a PhD student in our project. So this is about tipping points and the hysteresis curve for the Antarctic ice sheet, really derived from these highly resolved process-based simulations. And it's basically the experiment consists of a quasi-adiabatic warming. So global mean temperature change is translated into a regional surface air temperature and regional ocean temperature change, shown by these different temperature scales here. And the model is basically run into a quasi-equilibrium for very small steps of this temperature change, and thereby allowing to trace basically a hysteresis curve, just like you would do it for other physical systems that have multi-stability and memory effects and such things. Now, first, the y-axis shows the sea level relevant volume here. So, also on the right-hand side, it's a percentage of present-day volume. So what a basic finding is that at about 12 or 13 degrees of global mean temperature change, which is a strong global warming, but not completely unconceivable on business as usual emission pathways beyond the 2100, of course, so more into centuries after that. But there you see that the Antarctic ice sheet can actually be lost completely or nearly completely. So this percentage of present-day volume goes down to zero, leading to up to 55 meters of sea level rise globally, global mean sea level rise. So this is how the sea level volume is interpreted. Then, if you zoom in a bit more at more temperature rises that are more expected in the near future, you can look at this zoom in, this inset, and it shows that there's some at above 1 degree of global warming, the the hysteresis curve starts going down, volume starts to decline, and there's quite a steep gradient there at between 2 and 2.5 degrees, which corresponds to a collapse or part collapse of the Western Arctic ice sheet. So this is the first tipping point that is recovered here in this process-based simulation, consistent with other studies. And then a second temperature range with a large gradient is between 6 and 8 degrees of global warming, where parts of the Eastern Arctic ice sheet then start to collapse as well. And an interesting point here is that it's really a hysteresis that we find. So when you go to very high temperatures, like these 12 or 13 degrees here of global mean temperature change, and then turn back the temperature, it's clear that the Antarctic ice sheet doesn't follow the same path of recovery, but it takes much longer to recover. It takes the ice sheet then on the melting path, and it even takes global mean temperature changes up to -3 degrees compared to today to recover the full ice sheet, which really also raises some interesting thoughts about, I think, memory effects related to the past ice age cycle. It's really showing that the present state of the Antarctic ice sheet is probably a legacy of the last ice age cycles, and cannot be explained just by Holocene climate conditions alone. But this is, so this is the type of result that we can get from these very detailed process-based models. Maybe one additional brief point is that there are these vertical lines which go down from the hysteresis curve or up, and these correspond to even longer simulations where the system is run even further into equilibrium, where we see that the hysteresis curve by enclosed by these diamonds is smaller than the transient curve, but it's still there, and giving us confidence that it's actually a hysteresis curve, even though, of course, we cannot compute this model for infinitely long. So there's still some uncertainty, but also on theoretical grounds, I think it's quite conceivable that there is actually a non-zero hysteresis volume. But in any case, this is only a theoretical construct, which it's only a stylized type of experiment that we do here to understand how the ice sheet responds to these different global mean temperatures. So it's really for climate change projections, it's really this melting part of the hysteresis curve. The downwards part is the one that is important. The other one is more theoretically important, and maybe also for paleoclimate types of studies. So then building on this type of work, we were thinking about, so we were not only thinking about interactions between the tipping elements among each other, but also how tipping can feed back on general global warming and general Earth system properties. And one obvious thing that we thought would be important for the cryosphere is the albedo change that melting of say the Antarctic ice sheet, the Greenland ice sheet, the Arctic sea ice, or mountain glaciers would bring about. And this is this motivated some experiments that we did with an intermediate complexity climate model, an EMIC Clamber, Clamber 2, that is quite established here at PIC, and we basically changed. We emulated the melting of these different parts of the cryosphere by just changing the albedo of the land surface at these places and running the system into equilibrium, and then looking. We wanted to know what additional warming contribution due to this albedo change we would expect. Due to the tipping of these elements, and you can see this here in regionally resolved. And what one can see here is that the biggest effect on surface temperature is, as you would expect, close to these cryosphere elements. So it's close to the ice sheets, and it's close to the sea ice. But also when you sum it all up, you get quite a significant contribution. This, by the way, I said only albedo. I mean, this is what we put into the model. So we changed the surface albedo, but there's also other effects, other feedbacks that count into this overall temperature, this amplification of warming. That is next to the albedo feedback. There's also surface elevation feedback effects, and also cloud water vapor type feedbacks as they are represented in climate, which is of course in a limited way, but calibrated to the results of big process-based, process-detailed system models as used for the IPCC model intercomparison exercises. So what we see is that with 1.5 to 2 degrees of global warming, where we would probably likely on the long time scale lose these cryosphere elements. If we have this warming, we would expect an additional up to about 0.4, 0.37 degrees of warming because of these feedbacks induced by loss of cryosphere components. So it was important for us to get some kind of an estimate here. This is not too big, of course, but it's also not super small, given that people discuss a lot nowadays between about 0.5 degrees of global warming. So the difference between 1.5 and 2 degree futures in the context of the Paris Climate Agreement. So we thought this is about of the same order of magnitude. So it's definitely an effect that is relevant to look at, and it's not all of these effects are necessarily included in big Earth system model simulations right now. So it's always it turns out again and again in these types of studies, it's very important to tease out which of these effects, which of these processes are actually included already in big process-based system modeling studies used for the IPCC, and which ones are not. And I think this is again and again turns out to be important when doing this type of maybe more conceptual work. So now we would like to move more into the interaction between tipping elements, and this is something that I would like to approach first from a bit more conceptual, more theoretical point of view. So the idea is really that you could model interactions between tipping elements as people have done before by looking at two more stylized tipping elements which have such a cusp-like or fold bifurcation-like bifurcation diagram. So there's a certain region with bistability, and then there's two critical thresholds, and there's bifurcation-induced tipping. And the tipping elements interact by basically having the state of one tipping element feeding into the control parameter of the other tipping element, and potentially also vice versa. And the generalized model that is used a lot is this one here, a differential equation with a cubic term that seems to be the most simple form of such a fold bifurcation that you can find in the literature, and it has been used in different works, and now also in the catastrophe theory of the 70s and even earlier. I think such models have been studied, but in a more mathematical way. We found studies by, for example, Abraham from 1990, and also, for example, there's a study by Brummett et al. 2015, which uses this type of model to study tipping element interactions. So now let's move to this. There is a general form of these interaction tipping elements based on all these papers that already exist, can be written like this. So you can do this for n interacting tipping elements on a network, but let's start with 2. You have these this normal form of the fold bifurcation, and now here the parameters they are normally, if I move back, there are 3 parameters here. One is missing, so it can be A, B, and C. The B should be in front of the cubic term, and they describe the A and B describe the shape of this curve, and C is the critical parameter, which determines where you are in the bifurcation diagram. So basically, on which branch you are, and the idea is now when building this model with the interactions is that there's a coupling term as usual, and this coupling term can depend on the value generally of these 2 tipping elements, and you can see it as a part of the control parameter. So you can see it as the state of the second tipping element, say, is moving the first tipping element on its bifurcation curve by changing the effective value of the control parameter. That's one way to see it. And we've done this, well, let's go back. So we've done this with a very, and as others have before, in a simple way where we said this coupling function is linear. It's non-diffusive, but as it should be shown here, yes. So here the coupling function is shown on to the right, and this shows the case of unidirectional coupling with a linear coupling term, and so the coupling term in equation 1 is 0. In the second one, it's just a coupling constant d times the state of the first tipping element. So in this case, it's the first tipping element doesn't feel the second at all. So it's just the same, behaves the same as an autonomous, as a tipping element, but the second is influenced by the state of the first, and in a way such that the critical parameter of the second tipping element is effectively moved around by the first tipping element. And if we can look at that, so this is the set difference. Not point with my mouse. Oh, now I can. Maybe you can see my mouse. The critical parameter has this value for an isolated tipping element with these standard parameters, square root of 4/27, this is what we sometimes call the intrinsic tipping point. So this is what the critical thresholds that the tipping element would have without interactions. And if we add these interactions, it's effectively changing the value of this second control parameter. So you can just add that here, and in that way compute a value of the effective tipping point C2, which is actually effectively smaller than this square root 4/27, because here the coupling is positive. So you have to subtract d times x1 from this value. And so this means that the system, actually the second system, can tip earlier than it normally would due to this interaction. So in a certain sense, the tipping of system 2 is facilitated, is amplified by the tipping of the first element. And the pictures that are the phase-based pictures that are shown here are the phase-based flows for different values of the controller, and for a certain let me see, yeah, for a certain coupling strength, which is larger than 0 here. And you can see that, of course, depending on the value of these control parameters, there exists a different amount of fixed points, and the flow changes such that different types of course, very different types of dynamics are possible. And one way, one example system that where this has been studied is for example, the chain of lakes in ecology. So there's a number of papers, for example, by Martin Schäfer and others from his group, but also other groups where they look at the tipping of a lake, and then it's connected by a river to another lake, and then looking at whether the second lake or even further down in the chain lakes could tip as well. Now, what we try to do also in this paper, which is in review and in the archive as well, we try to classify the different possible regimes in parameter space in which different types of effects can happen. And this is a bit complicated, but let me just, due to time limitation, also just say that you can identify regimes where what we call a domino effect can actually happen, where the tipping of the first element can lead to a tipping of the second element. While there are some regimes as well, like this red one down here, where this is not the case. And this depends on the values of these critical parameters, the control parameters, coupling strength, of course. This is now we can also look at more settings of interest in climate setting, for example. So this is now a bidirectional with a negative feedback. So this is where one of the coupling strengths is positive and one is negative. And this an example where this is or seems to be the case in the climate system is the interaction between the Greenland ice sheet and the Atlantic Saharan circulation, because the Greenland ice sheet can the tipping of the Greenland ice sheet leads, at least for some time, to a large freshwater flux into the Atlantic, which should be a positive interaction in this sense here, because this facilitates the tipping of the thermohaline circulation. But on the other hand, the circulation leads to heat transport from the tropics to the Arctic to the Greenland ice sheet. So it should in turn dampen. That should be a negative interaction in this here. And we can then again do these types of plots where we look at different numbers of fixed points that exist for different values of the coupling strengths for these two couplings, and again find that is quite a that is. And when we look at the case where the coupling strengths are approximately equal, we can again look at this for just the two critical parameters, and we find again that there's a certain regime where domino effects, where the tipping of one can lead to a tipping of the other, can exist. But there's also other regimes where either this domino effect doesn't exist. So when both are not tipped and are far from the critical parameter, obviously this doesn't work. But there's also other regimes where they're a bit more complicated. And now the idea is, of course, and the challenge to extend this to larger networks of tipping elements. And I mean, of course, there's some work that has already been done. Maybe, can you guys hear me? Okay, good. So yeah, let's go through this quickly. I mean, this is we now wanted to apply these types of analyses to what we're actually interested in, whether even based on such a relatively simple model, it's possible to do some kind of risk analysis for under which conditions there can be anything as tipping cascades or domino effects in the system of climate tipping elements, and of course acknowledging that this is oversimplification of what is happening in the real world. So what we did is we studied generally how these types of generalized tipping elements behave on complex networks. So under which conditions, for example, which types of network structures, which types of coupling strengths, for example, you can get global cascades where the tipping of one element can lead to a tipping of a large number of other tipping elements, of a large fraction of the network. And turns out that you can study this with get some insights that there seem to be phase transitions in these networks where cascades can either be started or they are quite effectively suppressed. This is also not surprising. I mean, building on similar systems studied before and so on, but it was important for us to study this in detail. And we also found that's kind of the second paper here, which is in review still. The other is in PIE in press. In this review paper, we find that we study the role of important local mode structures. So it turns out that certain types of modes which involve feedback loops, but also so-called feedback, they exist in these networks with a high density. They effectively can lead to global cascade possible, basically. So they can basically create these phase transitions from non-cascade. So it's quite interesting structure in real world systems as well. For example, in moisture cascading networks in the Amazon or other types of networks where tipping is important. Now, the system that we studied, we focused on first was the a network from 2009 where they did a quite large expert elicitation to find out what experts thought about for example, what the probability is if one tipping is what is then the probability that another one will tip because of that. And they did quite a sophisticated statistical analysis of that, some methodology with uncertain probability ranges, so on and so forth. So it's something that we felt was quite useful, and we wanted to build on this, study these interaction effects. And just to go, this is also a paper which is currently in review. What we find, I mean, kind of, so this is again here down in the network of tipping elements that we look at. So it's Greenland ice sheet, West AMOP and ENSO. We put in okay, internet connection stable. I hope I stay in. So we took these critical temperature ranges of the encoded parameter C in model, and took this from the latest literature review, which we did for the with Stefan 2018 PNAS paper, and we took the interaction network and the interaction strengths and direction of interaction from the Kriegler due to where we really knew that the current literature is suggesting different things, so particularly on the direction of interactions. And so we used that to basically calibrate the network. And we also used timescales on which these elements are behaving to calibrate other parameters. So basically we can also calibrate this parameter A and this parameter B using the typical timescales. So for example, acknowledging that ice sheets change even more slowly than the ocean, and the rainforest probably can tip more quickly than an ice sheet, just given the internal timescales of these systems. What we did is a huge Monte Carlo approach. We took into account all these huge uncertainties we have in temperatures for tipping, the interaction strengths, even the direction of interaction in some cases, and the timescales. And we sampled that using millions of runs of this relatively simple model. That's why that was possible. And one first order result that we get is that if we change the global coupling constant, which we use as a control parameter here, because this is something you can it's not easy to constrain that to know basically how important are the interactions around and the processes and the dynamics of the tipping elements themselves, so the internal dynamics. And that's why we have this coupling constant, this global coupling constant parameter, which basically says there's no interaction, so interactions are not important at all compared to background climate processes and internal tipping dynamics. And one means they are very important. The interaction is important. These other things. And what we find is that we can look at how the effective thresholds, the effective tipping points in temperature space change with this global coupling constant. And the interesting thing is that, for example, here this is panel B. For West Antarctica, you see that this effective tipping temperature is because of the interactions, because there's a lot of amplifying, tipping, enforcing interactions there. While for Greenland, this temperature range is increased with coupling strengths, which is among others that I talked about earlier, but with huge uncertainties. So we see the uncertainties are really huge, so we cannot. Also interesting, while for the West Antarctic ice sheet, the uncertainties stay approximately the same there. And there's also other for these other elements in this group, the AMOC, ENSO, and Amazon. There's really a truly destabilizing effect of the interactions. So we see that the effective tipping temperature for all three. So we can say already here, based on this analysis, on these, considering all these uncertainties and acknowledging it seems that at least what we can say is of approach. There we can say that these interactions of the tipping elements tend to be rather destabilizing rather than stabilizing, because there have been papers published in the past that claim that for some of these interactions they might be actually stabilizing, even for the whole climate system, even at least potentially. But here we show, with the exception of Greenland, this seems to be not the case, but there seems to be rather, at least in this simple model, a destabilizing effect. And this further and look at this network analysis more, from a complex network perspective of tipping elements in case that we extract. And what we looked at was that what is the fraction of simulation runs in this huge Monte Carlo ensemble, where, for example, Greenland was an initiator cascades, and in how many cases was it a mediator? So was it just part of the cascade, or potentially transmitting the cascade end of the globe to the other end? And it turns out that the large initiators tends to be, in many cases, 40% of the simulation runs is an initiator of the cascades. This is the tipping element that basically tips first, and then others follow when temperature is increasing. While others, like the AMOC or the Amazon rainforest, they are not initiators at all, but they tend to be part of many cascades. So they rather act as transmitters of cascades. And again, this is probably due to the particular structure of this interaction network, which has to do, of course, also with the geographical locations and this issue of what is located in the polar regions, what is located more in the tropics. So this is basically first results which to me show that it's interesting to look at these types of dynamics from a network perspective in more detail in the future too. And maybe a last teaser on these types of results is this one. So this is where we now show, this is again this parameter study now for different levels of global warming and different levels of the global coupling constant. And the left panel shows what is the average number or the average number of tipped elements in these different parameter settings across this huge ensemble that we are studying, or these uncertainties that we study. And it turns out that there's a clear risk gradient between for higher coupling strengths, even 1 and 3 degrees of global warming, where we go from no tipping to all elements are tipped, and the coupling constant has a strong influence on this. So for weak coupling, this risk gradient is at much higher temperatures than for large coupling, and this is a nonlinear effect, as you would probably also expect. And it also turns out on the right panel, we see the uncertainty, the standard deviation of tip elements for these different parameters. And it turns also out that the largest zone of uncertainty due to all these different parameters and uncertainties that we study is really between 1 and 3 or 4 degrees. So this is really exactly the region which is most relevant for political discourse right now. It's kind of this Paris range between 1.5 and 2 degrees. This seems to be the zone of uncertainty also for these types of dynamics that we would avoid under all costs, like triggering global tipping cascades. So quite interesting, I think, to follow up on this with more process-based models. And again, it's really important for maybe people like us who are doing to tease out which of these types of dynamics are already in process detailed Earth system models and which ones are not, right? Okay, so let me very briefly go to these social tipping points and then wrap up. So I need to get rid of this group chat. Unfortunately, I don't see my mouse pointer anymore. Okay. Briefly wrap up. We also look at social tipping points, and we did an expert elicitation on this. The idea is that it's important, social tipping important as a solution strategy to climate change, because right now there's a lot of discussion about this problem that since 30 years, but nothing really has happened. Only very slowly with Fridays for Future, things have now started moving, at least in Germany. I can say we have this Klimapaket, this political package, which is still not very ambitious, but at least it's there. And we did this expert elicitation asking people to identify what potential social processes could have the potential to produce tip dynamics, which could lead to a rapid decarbonization as it is needed by the Paris Agreement. So kind of decarbonizing effectively, net decarbonization by 2050, that is in 30 years from now. And there's all these different tipping elements that were identified, ranging from financial markets to norms and value systems. And we are also very interested in learning more empirical elements with social scientists in the Dominoes project and also others, and also trying to model some of these dynamics using, for example, adaptive network models where agents and network structure can co-evolve, and we can study how this spreading processes of behaviors, opinions, or social norms can take place, basically leading to macroscopic tipping behavior in societal dynamics, which is again important for the Earth system. And now this is kind of then the wrap up. It's a lot of my work over the past years is about trying to close the loop in Earth system analysis, bringing together these societal dynamics like social tipping points and nonlinear Earth system dynamics like climate tipping points. We've built this Copan Core modeling framework, which is now in press in Earth system dynamics in the journal to facilitate these types of modeling studies. And in the Dominoes project that I mentioned at the beginning, we are working on basically the potential feedback interactions between these interacting climate tipping elements and social tipping elements. and how this all unfolds. And we're working on some modeling studies on this as well. And with that, I would like to summarize. So I think it's important to study the dynamics of tipping elements under global warming, because there's potentially very large impacts to human societies. The same holds for, of course, maybe even more for potential tipping cascades or domino effects. But the interaction of tipping elements and the potential for such cascades is still understood, even particularly with process-based models. So we really need, I think, persistent models in perspective, which can be used to study these types of questions.
No questions?
Hello. I've got a question.
Hi, Peter. Okay.
Okay.
Yes, thank you. Very, very nice talk. Very interesting. I'm just wondering if you've been considering at all the influence of stochastic effects at all. So as far as understood, yeah, that's you're looking at deterministic models. Is that true?
Yeah, and this exactly. So what we've done here is the model itself is deterministic. Yes, we haven't included noise to keep things a bit more simple yet to that point. Yeah. I mean, what I should add, I'm not sure if the internet connection is stuck again, but what we've done is this. So we haven't done we haven't studied stochastic processes in this more realistic setting with this what we call the Kriegler network, but we've done it with more in a more theoretical setting. And a bachelor student is still working on that. So how these tipping cascades behave on networks if you allow for stochasticity. And there's also some interesting results there. I mean, more mathematically interesting, maybe in terms of how you get some kinds of random walks in that system when the stochastic component interacts with the deterministic part and the nonlinear, the strong nonlinearity in these individual systems.
Thank you.
I think there's a note for you in the group chat from Michael. If you open that up.
Yeah, exactly. So maybe let me go back to the. Michael's referring to the. So where is it?
Hi. Yeah, that was the Antarctic hysteresis.
Yeah, the Antarctic hysteresis, right? So
that's a blank screen for the moment, but it's probably coming. Yeah, we see your screen.
Yeah.
That's because it's a
now?
diagram which is often shown, and we see its regional surface air temperature change. Because when we see 10 degrees, oh no, by the way, I see no, that was too quick to me. The upper scale is regional surface air temperature, and the lower scale is global mean temperature change.
Yeah, exactly.
Okay,
exactly.
that clarifies things. Okay.
But you're right. It's important to say that always. That and we struggled quite a bit to try to make it in a way that people can see these both scales, right?
Okay. That's something which is easily forgotten. Is that of course polar temperatures is 1.5 or almost 2 times the global average. All right, that was just an observation.
Okay, yeah, thanks a lot. It's more in the chat. Let's see. The temperature. So there's a question on the temperature. So the temperature for the Antarctic hysteresis is that's a parameter. So I mean the regional surface air temperature is imposed as a boundary condition, and also the regional ocean temperature. So this the regional surface air temperature interacts with the surface of the land surface of the ice, and the ocean temperature is important for the shelf processes that are modeled. But of course, the model has a fully dynamic thermodynamic part to it, which is doing the internal temperature in the ice. This is, but the outside driver is fixed. We don't have it coupled to a
Just,
model.
yeah. Well, I don't know whether it's relevant at all, but just as a note, so within our work package for TIPES, we are currently setting up a problem of optimal decision making, and we play a little bit with this Antarctic hysteresis phenomenon, also the Greenland one, and we use a very toyish model. It was made by Frank Patin, you know, this Belgian glaciologist,
Yeah.
who has made a number of ice sheet models, and one we use is a much simplified version of this more complex. Well, I mean, it's a very simple model, but it has enough degrees of freedom to represent this hysteresis. And I see that the boundaries which are simulated by that very simple model are more or less at the same place, and the hysteresis has more or less the same shape as this more complex setting. But as you say, here there is the whole issue related to the ice shelves, which is not captured by the more simple models.
Exactly, and these the ice shelves turns out are very important for the dynamics. So they can hold back ice flow from the interior by these buttressing effects, and but also a loss of ice shelves can really lead. There are these strong reinforcing feedbacks like the marine ice sheet instability, and maybe others that are relevant there, and that play a huge role in these tipping behavior that we actually see in this graph. So these temperature ranges with a strong gradient, like the one in the inset and the one at like 7 to 8 degrees of global mean temperature change, they are mainly driven by this marine ice sheet instability, where different basins, ice basins in Antarctica start to get into this instability and empty relatively quickly. And it's more about, there's several different basins which are tipped one after the other. So it's really like Antarctica is actually not one tipping element, but it's a collection of interacting tipping elements itself, which are the individual tipping elements, you could say in a way are these different ice basins. Okay, there's a question on early warning. Yeah, this is an important point by Richard Timber here. So if you look at these multi-element models, it's actually quite, and I think it's still an open question. So we are currently we are working on this actually, and on the possibility for early warning for tipping cascades. And it turns out that at least currently it seems that since it's not really possible to find using this in basically properties of the eigenvectors and eigenvalues of the Jacobian matrix close to a critical transition. That seems to not work because there's different types of cascades, and in the cases where it might work, it's would be a cascade, and in other cases it's difficult to find anything but for the tipping of one element itself. And so we think this is still inconclusive, and I think more definitely it's worthwhile to look into this more. I think, to me, intuitively, what is important are if you have feedbacks between tipping elements, so bidirectional couplings or higher order loops, it might actually be possible to find early warning for tipping cascades, because the information is somehow coming back to one point where you might measure an early warning signal, and basically information on the state of other elements might come back, and you might be able to use that maybe using some nonlinear methods. There's some possibility, there's a literature, big literature on spatial early warning signal, might be useful in that context. And also, it looks a bit on model driven early warning signals. So not the one that is about basically these correlation variance type of thing, but where you actually might work better as well, but we haven't explored that.
Thank you, Jonathan. I think it's very interesting. I think it's a very interesting view of things. I'm trying to think of things that we can do. I'm a GCM modeler, so I'm trying to think of how we could do some experimentation in this area. I suspect that probably the best thing to do would be to identify some kind of two-element systems where there's where we think there's a significant chance of some kind of interaction going on, and design some experiments around something very simple rather than going to the kind of multi-element thing initially. And the reason I'm interested in early warning is because certainly from experience with the AMOC, I'm pretty skeptical that these probability, like these burning embers diagrams, that we'll really be able to anytime soon create versions of those which have probabilities associated with them which we really think are scientifically robust. So the early warning gives you a different perspective on how to deal with the risk. And so anything around identifying observable properties of the system that suggest that we're going in that direction is a kind of a different approach, if you like, to managing the risk. But I think maybe if we think about some simple kind of two-element cascades, that might help us design some GCM type experiments. Thank you.
Yeah, thanks a lot. I really interested in doing these more process-based studies with Earth system models, because and then, as you say, early warning is a way to look at the risk maybe in a better way. And the Greenland AMOC pair is quite interesting, and the triple of Greenland, parts of Africa, and the AMOC, because there you don't need biosphere model components, which are sometimes still complicated. In there it's even harder to simulate tipping for the more physical climate systems, and it's also more disputed whether there is tipping at all. But for the ocean and the ice, my feeling is that it's more, we can be more them together is probably a good way to go. Yeah, so there's another question on the permafrost. Yeah, so I can go back to that. That's kind of this burning embers picture again. So the right, according to this type of picture, this picture comes from this overview paper by John Scheinhuber and Ricarda and Stefan Ramsdorf from 2016. And you're right. I mean, my current reading of this literature is also that there. I mean, I'm not an expert on permafrost at all, but I also, my impression is that recently a number of papers are coming. The processes that lead to faster than expected melting and feedbacks, but it still seems to be that it still seems to be relatively open. Right. It's maybe someone else can say more about that. So there's another question by Alex. Ah, right. Yeah. Hi, Alex. Yeah, the validation of the couple tipping. That's right. So I mean, I fully agree. This is, I mean, I think what would be an interesting way to go is to look at paleoclimate potentially, where there has been some work reported of cascading transitions. Paleoclimate might or might not be likely explanation for what has been observed in the paleoclimate record. And we could for some of these, we might be able to test what types of explanations basically these models that we've put forward here can deliver us. So what can they certain real-world observations in a meaningful way? But I mean, I think up to that point, I would think it's really more to be seen as it's a risk analysis on trying to propagate a lot of different types of uncertainties and with certain assumptions like this simple linear coupling, for example, and the lack of background climate effects that just have to be taken into account when you do this type of modeling. So it's nothing that we easily can validate, I think.
Okay, thanks, Jonathan. Very thought-provoking in any case.
Yeah, thanks. I mean, always looking forward for ideas, on how to move forward with these types of analyses.
Okay, that's good. Thank you so much, Dr. Dongus. And thank you everyone for joining us. Yeah.
Thanks for your interest. Bye.
Thank you.